Hello everyone. Today we are going to dive into one of the most fascinating topics in the distributed system, the consensus mechanisms. Imagine a system where there are hundreds and thousands of computers working together all around the world. But the question is, how do they remain in sync even when there are network issues? Or what if there might be some computers who might be compromised? This research paper, The Many Phases of Consensus in Distributed System, written by John Turek and Shasha, breaks down the core models of consensus that help us to see and understand how these mechanisms work, even under tough conditions. So, stick around to see how these concepts bring complex ideas into the life. So, what exactly is distributed system? It's a collection of independent computers that work together to achieve a common goal. But here's what it gets tricky. The challenge is consensus, ensuring that all the nodes agree on a single value or a decision despite the failures or even a malicious behavior. But why is this so crucial? Consensus ensures that there is a data consistency, reliability, making fault tolerant and highly available system possible. Think about blockchain, distributed database and cloud computing. They are all dependent on it. Now let us talk about a fascinating theorem by Fisher, Lynch and Patterson. They prove that in a completely asynchronous system with unbounded message delays, achieving deterministic consensus is impossible, even with just a single faulty process. Imagine trying to get everyone to agree when a message can be delayed forever. An adversary could keep the system in a state of indecision forever. So, this highlights the limitation of asynchronous systems and pushes us to find a better solution. So, to navigate around these limitations, some researchers like Dolliff, DeWork, and Stockmeyers proposed a certain type of parameters. Let us break it down. The first parameter is a synchrony, which says how predictable are these message delays. The second one is the message ordering, which says, are these messages delivered in the order that they were sent? And the third parameter is the failure model, which says that what types of failure that can occur. So by tweaking these parameters, we can design practical consensus protocols like the Paxos or the Raft that rely on specific system assumptions. Next up is Maurice Hurley's work on shared memory. He introduced the concept of consensus number, which measures synchronization primitive's ability to solve consensus problem. But shared memory alone isn't enough in a synchronous system. Techniques like compare and swap helps to bridge the gap, playing a crucial role in real-world applications like database systems and distributed file system. Now let's get into the Byzantine general problems, which was introduced by Lamport, Shostak and Thies. Byzantine failures involve malicious nodes that sends false information. For consensus, we need two things: network connectivity and a majority of honest nodes. So we can also see this in a real world example like digital signatures and cryptographic techniques, blockchain systems which uses consensus mechanisms such as proof of work or proof of stake so as to ensure that there is security and integrity. The main goal of this research paper is to investigate limitations of achieving consensus in a asynchronous distributed system. The paper also aims to prove that the deterministic consensus is impossible in completely asynchronous systems even with a single faulty process. The foundation also leads to the design of fault-tolerant algorithms and guides development of distributed systems. The core finding here is the proof of impossibility of deterministic consensus in an asynchronous distributed system that has one single faulty process. And the novelty over here lies in the rigorous mathematical proof techniques that has been used to analyze the fundamental limitations of the distributed systems. Time for a technical deep dive. The methodology involves a proof of contradiction, showing that any proposed consensus algorithm can be exploited by a faulty process. The key concept for this includes is first, asynchronous system, which contains unbounded message delays. The second one is the faulty process that deviates from the protocol or fails. And the third is bivalent state, which is a system that can reach either of the two decisions. Let us evaluate the strengths and limitation of this paper. The strengths include its rigorous proof of fundamental contributions. However, it focuses specifically on failure model, that is the crash failures, and it does not consider more complex one like the Byzantine failures. Future directions involve the exploring the impact of partial synchrony, probabilistic algorithms, and developing resilient consensus protocols. So, in my opinion, the impossibility result is the fundamental limitation of any asynchronous systems. But understanding these principles help us to design more robust systems. So there are some follow-up questions that might need to ponder about. The first one is that how can we relax assumption in order to achieve a practical consensus? The second one is that what are the trade-offs between the different algorithms? And the third one is that how can we design algorithms that are resilient to both crash and Byzantine failures? To wrap it up, Fisher, Lynch, and Patterson's theorem reveals the limitations of asynchronous distributed system, and understanding this is very crucial in designing practical and reliable systems. By relaxing assumptions and exploring other alternatives, we can tackle the challenge of asynchrony. Thanks for joining us on this deep dive of consensus in distributed system. See you next time.